We will now discuss the cross product, which we also call the vector product or the outer product. Now, this is an example of the rotational dynamics. So, in this one, we will rotate one vector along the other vector. We did in the dot product, we found the contribution of one vector along the other vector. While in cross product, we will find the swept area, then how much area will be swept by one vector if it is rotated along the other vector. For example, we are having, let's say, a coordinate system, again a two-dimensional coordinate system, and this is all negative x, this is positive x, negative y, and positive y. Now let's say we are having a vector, and that vector is in this direction, as we considered previously for the dot product. So the same vector combination we will consider here as well. And there is another vector which we call vector b, and the angle between these two vectors is theta. Now in the dot product, we found the projection of one vector along the other vector, of this on this or this on this. Now in this one, in the cross product, we are having the rotational dynamics. So we will rotate this vector along this vector or this vector along this vector. So let's first rotate this vector along this vector. So now, if I rotate this vector along this vector, then this vector will sweep some area. And how much that area will be? That area will be if I consider this vector here, means keeping the angle the same. This vector here, and then this vector I consider here. So it will give me this much area, which we call the area of a parallelogram. So this much area will be swept. Now when I will move this one, will rotate this one along this one, the area which is swept will have this direction, the thumb direction. And if I will rotate this vector along this, then it will have the inner face of the board and it will be into the board. So it means that the product of them is coming out to be a vector quantity, is the rotation this way gives this direction, while the rotation that way gives inside of the board direction, into the board direction. Now how much this area is? This area, if I consider a triangle, and a triangle is such that it is like this, and let's say this is B, and what is the area of this triangle? If this height of the triangle is h, then the area of this triangle is half BH. We know this thing, that the area of this will be half times base into height. Now here, if I split this into two triangles like this, then this is one triangle, this is one half BH, and this is another half BH. So half BH plus half BH will give us BH. BH means that we will have to multiply this A, which comes out to be the base here, and here it is this base, and then the height of it. So here the height comes out to be this one, and for this it will come out to be this one. So both are actually the same. So it means that if I find out this height, then I will just write that area is equal to this one. So A, and I rotate this one along B, cross means rotation, and this will be equal to BH, means the base. Here the base is A. So base is A, and then this one, the height. So the height, if I find out this one, then how much it is? You know that this one will be B cos of theta, and this one will be B sine of theta. This height. So this one comes out to be B sine of theta. So the two triangles are being added, which is a parallelopied or parallelogram, and half BH plus half BH give us BH, and we got that we will just multiply B in our case is A here, the base, and H is actually this height, which is equal to B sine theta. Now another thing additional here is that when I rotate this one along this, then I get this direction. Let's say the direction which is coming out of the board, and out of the board direction I denote by a dot here, and into the board direction I will denote by cross. Now these are known to us from the magnetic field calculation as well, that this is the arrow direction. So when the arrows comes out, then we can locate it and we see the top of it, so it is dot. And when the arrow goes into the board, then the back of the arrow is having cross, so it is going into the board. So when we rotate A along B, then we will have the dot here, the dot direction. And when we will rotate A along, when we will rotate B along A, then we will have, these are just number, and we will have sine of theta, and we will have this direction. Sometimes this one is out of the board and this is into the board. So it is better, instead of writing it like this, I write it is AB sine of theta and n hat, and then this one will be AB and sine of theta and minus n hat. So this is equal to AB sine of theta n hat, and this is equal to minus AB sine of theta and n hat. So from here I can say that cross product is not a commutative relation. So A cross B here is equal to B cross A, but with a minus sign. And now we will consider some limitations of this. This theta is like the dot product is having its range greater or equal to 0 and less or equal to pi radians. So we are having A cross B. Now this one is, we say that why we use sine theta in the cross product. We are not using it, but we know that area of a triangle is half BH, and here we are sweeping this vector along this, and it gives us the area of parallelogram, and we can split it here, and there are two triangles, so half BH plus half BH will give us BH. Now B is the base. Here our base of this triangle is A, and height comes out to be B sine theta. So we have not used this one, but this one comes out to be the height. Similarly, the height here also comes out to be b sine theta, and we have written it like ab sine theta. So this is one of the example of rotational dynamics. If theta will be equal to 0, means this vector is exactly over this vector, or they are parallel to each other, then we cannot rotate one vector along the other vector, and that's why the rotation will give us 0. And if I put here for theta equal to 0, then sine 0 is 0, and I will get A cross B is equal to 0. If I will be having theta equal to 45 degree, for example, then I will get A cross B equal to AB, and sine of 45 is 1 by square root 2. So it will be this much. So I will sweep this much area, and if theta will be equal to 60 degree, then A cross B will be equal, sine 60 is half, so it is AB over 2. If theta is equal to 90 degree, then I will have A cross B equals to AB, and sine 90 is equal to 1. So this will give me the maximum area here. Like if I have this vector like this and this vector like this, this is A and this is B. Now it will make the shape like this, means this much area will be swept, and this area I know that it's like a square, that one side is A, the other side is B, so the area comes out to be AB, and we are having the area equal to AB. So this way we can cover this rotational dynamics, and this will be the maximum area, because we know that sine of theta is varying between +1 and -1. So for this quadrant, when I consider for this quadrant, then it is varying from 0 to 1. So when vectors will be parallel to each other, I will have no swept area, and when vectors will be exactly perpendicular to each other, then I will have the maximum swept area, this one. Now I can consider this with an example, and the example, let's say I am taking the example of torque. So torque is equal R cross F, and this is equal to, now R is the moment arm, F is the force, and tau is the rotational force. So RF in sine of theta, and this is in some direction. Now this is, let's say for example, a point, and from here to here is a moment arm. Let's say this may be a door or something like that. Okay, let me mark this thing like this. So it's somehow a door like. Okay, now this is the moment arm. If my force will be exactly perpendicular to this door, then I will be able to turn this door the maximum. Means when R and F, the F which is like this one. So let's say the F is in this direction, that it will make, let's say, in this direction, the perpendicular direction means it is perpendicular to this one. So in this situation, I will have maximum angle here, 90 here, and I will be able to turn it. Now if the force is in this direction, means anti-parallel to this one, or I will be dragging the door exactly along the moment arm direction, I will not be able to turn this door, to rotate this door. To rotate this door, the force will be at some angle to this F, between means theta less than, for example, less than or equal to 90, so maximum, and greater than 0. So when theta will be greater than 0, then I will be able to rotate this door. So the rotation here, there will be no translation but only rotation. Similarly, we can take the example of angular momentum R cross P. We can take other examples as well. Now R cross P, P is the momentum, the linear momentum, and this is the angular momentum. Now this angle will, this cross product will give rotation in a certain direction. We can take the example of screw, and the screw example is very good to consider. So it's, let's say it's a screw, and okay, now if I will move this screw in this direction, then it will go into a surface, and if I will rotate it this way, then it will go out of this surface. So the screw example is very right to consider, that moving it in this direction will move it in, and moving it in this direction will move it out of this. So its rotation will occur in both cases, but in one case it will go into the surface, and in the other case it will go out of the surface. And here we are having the cross product. Now in component form, then in component form we know that F or vector A is, for example, 2nx plus 3ny plus 4nz, and our vector B is, let's say, 3nx, 2ny, and 1nz. Now if I want to find their cross product, then their cross product is actually equal. I will consider the A cross B equal to, here I will consider x, y, and z, and here 2, 3, 4, and here 3, 2, 1. And now I will multiply this determinant, and it will give me a value. So if our vector A is this one and our vector B is this one, when x is multiplied with x, then these are the inner components, and it will give us 0 because they are parallel vectors. The angle between them is 0, so these components will give us 0, while when x is multiplied with y, then it gives us the z unit vector, and z is out of the plane of x and y, and due to that reason this one is called the outer product. The inner product, the inner components are giving 0, unlike the dot product, while the outer components actually give us the results. That's why it is also called outer product. So as a summary, The cross product gives us rotation, while the rotational dynamics, while the dot product gives us the translational dynamics. When we multiply as a dot product, then cos theta was not coming by our choice, but cos theta was actually due to that component here. And sin theta here is not coming due to our choice, but actually it is coming with the height vector. That's why we use cos theta over there and sin theta over there from our mathematics, because we have defined it like that. So these are the examples of translational and rotational dynamics. Thank you.